All right, these notes are going to be on work. So work is if an object is moved in a direction and with an applied constant force, then work equals force times displacement. So if an object is moved in a direction with an applied constant force, then work is the force multiplied by the displacement. And the displacement means how far the object is being moved. If an object is moved along a straight line by varying force, then the work moved from A to B is going to be the integral. And so if you think about this, the derivative, so we're finding the antiderivative, right? So the derivative originally would have been an instantaneous rate of change, and if you have a varying force, then you have a varying rate of change, a varying applied pressure there. So to find the work, you would want to undo that to be able to get back to your derivative, or undo this integral here. All right. So here I want you guys in your notes to highlight this constant force versus varying force, because it makes a big difference. Either you're just using a simple formula or you're doing an integral, and that's going to change quite a bit in the problem. So we have two different laws we're going to look at. One is Hooke's law, which is about compressing or stretching a spring. And the formula that we use here is that force equals K times D. So the K is the constant of the spring, and that depends on the spring. That would mean that a really tightly coiled spring that's got really thick metal would have a much bigger constant than a spring that's really thin and easy to kind of move around. So this depends on the spring. And then the value for D is the distance that you compress or stretch the spring. And this force right here is varying. So this is where we would take this formula that we've got right here, and this formula for force would be plugged in here, and you'd be taking the integral of it. So we would say the work is the integral of K times D. We would be plugging the force in right there. All right, the other law that we're going to look at is Newton's law of universal gravitation. So that is the force of attraction between two objects. The force of attraction between two objects. So here, force is G multiplied by M sub 1 times M sub 2 divided by D squared. And we'll go ahead and call that K divided by D squared, so that these three things multiplied together are how you find your K value. So the D is the distance between the two objects, and you have to think about what your objects are. If you're talking about one tiny eraser and another tiny eraser, that might be a little bit easier to say what your distance is. But if you're talking about the distance from a person to a calculator, do you measure the toe of the person? Do you measure from the person's eyeball? Do you measure from the person's right pinky? Do you measure from the front of the calculator, from the back? So measuring distance between two things is kind of hard to be consistent with unless you have a way where you say every single thing has to be measured this way. And that's what they've done here, is they actually measure the distance between the center of the masses. And that's how they make it consistent, so everyone's doing the same thing. So between the centers The m sub 1 and the m sub 2 is the mass of the objects. So two different objects, mass of the first one, mass of the second one. And then g is the gravitational force. That's 6.670 times 10 to the negative 8th power. So that's the gravitational constant. And like I said, these are the things that work together to find the k value. All right, again, this force here is a varying force. And so that means that this formula right here is going to be plugged in right here, and we're going to be integrating it when we figure out the work for this. All right, so here are the examples that we're going to do. It says determine the work that's done in lifting a 50-pound object 4 feet. So here this is constant. This is not anything varying. Technically, I guess it would be varying a little bit because your gravitational pull would change slightly in the 4 feet, but not enough. We would say it's a small enough number of difference to be something we can ignore. So we're going to say that this is a constant, and so this is work is force multiplied by displacement. So the work is the force, which is 50 pounds, that's pulling down, multiplied by your displacement, which is 4 feet. And so the work is going to be 200 foot-pounds. There's our units there. So you'll notice that when you do work, you're going to have units like that always. All right, next, a force of 750 pounds compresses a spring. So we're using Hooke's law here. 3 inches from its natural length of 15 inches. Find the work done in compressing the spring an additional 3 inches. So we have to find our constant first, the spring constant. So I'm going to say the force is 750 pounds equals k multiplied by 3 inches. So that's the distance that we worked with the very first time. And so I'm going to go ahead and divide that by 3 inches. And that means that the constant for that spring is 750 pounds, not 750. Got to actually divide that. Sorry. 750 divided by 3 is 250. So that's 250 pounds per inch. So now that I've figured out what my k value is, now I can go back and say I'm going to use work equals the integral. So I'm going to compress it an additional 3 inches. So right now it's compressed at 3, and if I condition it, there's 3. And if I compress it an additional 3, then it would be compressed by 6 inches total. So I'm going from 3 inches to 3 more. And then my formula for force here is k times d. So k is going to be 250. The d value is the distance of 3 and the distance of 6. I'm going to put an x there because that's changing. I'm plugging different numbers in. And then this is a problem that you can go ahead and integrate on your calculator. And what you get here is 3,375 inch-pounds. All right, for our next example, it says it takes 20 foot-pounds of work to stretch a spring 6 inches from its natural length. How much work would it take to stretch the spring 10 inches? So again, we're using Hooke's law, where we've got force equals k times d, so we know we're going to use that at some point. They also talk about work that we have. So it says 20 foot-pounds of work, that's W. So since they're talking foot-pounds, that means that our entire problem needs to be in feet. So 6 inches would be 6 out of 12, so that's 1/2 of a foot. 10 inches would be 10 out of 12, so that's 5/6 feet. So if we set up the problem to use the information that they gave us to start, we would say that work equals, and they gave us information about stretching it from no stretch at all to 6 inches. So we got no stretch at all to 6 inches. and this is going to be k multiplied by x. So k is that constant for the spring, x is how far you're stretching it, and x would be like where we're plugging in the 0 and the 1/2. And I know in this problem that the work is 20. So I have 20 foot-pounds equals, and I can go ahead and integrate this. This would be 1/2 k times x to the second, and I'm going to be evaluating that from 0 to 1/2, and that's how I'm going to solve for that k value. So I'm going to go ahead and multiply this 1/2 over to the other side. That gives me 40 foot-pounds equals k, and I'm putting 1/2 in for x. So 1/2 squared is 1/4, so that's 1/4 k minus, if I plug 0 in, I get minus 0k. So 40 foot-pounds equals 1/4 k minus 0k. And I can go ahead and multiply 4 to the other side, so I get 160 equals k, and the units on that was foot-pounds. Okay, so now I can go back and see what it's going to take to stretch the spring 10 inches. Now it doesn't say 10 additional inches, it just says 10 inches total. So we're going to start from no stretch at all to a stretch of 10 inches, and then I have the k value multiplied by the distance we're stretching it, and that's where the x is being plugged in. And so when I type this in, I find that the work is approximately 55.556 foot-pounds. All right, a space module weighs 15 tons on the surface of the Earth. How much work is done in propelling the module to a height of 800 miles above the Earth? Use 4,000 miles as the radius of the Earth. Do not consider the effect of air resistance or weight of the propellant. So here is the Earth, and that's 4,000 right there. And the space module starts on the surface of the Earth, and then it goes out 800 miles above the Earth. So we have two different things. We have our space module and we have the Earth itself. And the center of the mass right here is a distance of 4,000. So that's what we're thinking about with our distance. The d, remember, if you guys remember, was the distance between the centers. So if we look at this, we have the universal law, Newton's law. So that was k over d squared. And our force here is 15 tons. That's how much it weighs. We don't know what that k is, that gravity times the mass of the one times the mass of the other. We can't use g times m1 times m2 because they didn't tell us the mass of each of the objects, so that's why we're just using k right now. And the distance between the centers is going to be the center of the Earth to the center of the space module, and so that's 4,000. So I'm going to go ahead and do 15 times 4,000 squared, which is 24 with 7 zeros after it. Let me think about how you would say that out loud. There's 4, 5, 6, 7. So 240 million equals k. Yeah. All right. So now we can go ahead and figure out the work that's being done. So the space module started 4,000 miles away from the center, and the center is going to be 4,800 miles away once it has moved. And then we're using this formula here, so our k was 240 million divided by x squared dx. And then when you plug in this to your calculator to figure out what the work is, it's going to be 10,000 mile tons. All right, and I'll go ahead and leave the last two for class.